Right, today we're going to look at the sine law. So the sine law is how we solve any triangle. Any triangle at all. It does work in right angle triangles. It works in every triangle. So we use capital letters for each vertex, right? Capital letters. Those are my angles. So that's how we label each vertex. And then what we do is we make sure that the side opposite from it, so A looks over here, so that becomes little a. Big B looks over here, so that's little b. And big C looks over here, that's little c. So the lowercase letters, that's my side lengths. And we organize it this way because the sine law says that this ratio of sine angle over side equals this ratio of sine angle over side equals this ratio of sine angle over side. And as long as you have two of these, only two fractions required for solving. So let's do an example and figure it out. Sound good? Sounds good. So here I have the example from the textbook. So from page 312, Albert is 7.8 meters from a balloon. Belle is 5.9 meters from the balloon. If the balloon is in the air and the angle of elevation from Albert is 36 degrees, we're going to assume both people on the ground. We want to draw it and then solve for the distance between the two people. Okay, sure. Well, here's my ground. Ground. Here is Albert is going to be A for Albert. And here is B for Belle. Sure, we'll put her over here. Why not? And I don't know, here's my balloon. All right. So then Albert, we're going to say is 7.8 meters away. Our angle of elevation, so we're told this angle in here is 36 degrees. And the distance to Belle, we said it was 5.9 meters. And then we have a triangle. Is that the only way to draw the triangle? Well, did we specify? What if Albert was here? The balloon was there, so we still got our 36-degree angle. Well, what if Belle is here? Notice how this one and this one do not look the same. Interesting. Can we solve it? Well, let's think. So let's see. If this is capital A, this is my little a here. If this is capital B, this is little b here. And we'll just call this one C because, so then this is little c here. So if I want to figure out this distance, okay, then that means I need one pair of angles inside, which is good. And then I need another pair of angles, and sides. I don't know anything there. And, I know that. Okay, so let's set up our fraction here. What do we got going on? Sine angle over A equals sine angle over side equals sine angle over side. So what does that mean? What do I got? So I've got sine 36 over 5.9. So that's a good fraction to use. And then I have sine, well, I don't have an angle for B, but I do have a side length for B. And then, let's see, sine, I don't have an angle for C, nor do I have a side length in the bottom, but this is what I need to find, right? That's what the question's looking for. Oh, we're going to have to do a lot of work here, people. A lot of work here. All right, first off, we need to solve for angle B first. So to solve for angle B, and we have to solve for that first because that's basically all I have available to me right now. Let's cross multiply. So if I cross multiply here, I've got sine B equals 7.8 times sine of 36 degrees, all divided by 5.9. Throw that in your calculator, and you'll get a great big giant decimal. So I get a decimal of 0.777. Don't round it, don't remove it, don't do anything. To bring sine to the other side, remember you have to do sine inverse. So as long as you don't clear it out of your calculator, you can just input your answer back into it. There's usually a nice ants button. Second function sine, second function answer, and I get 50.99, so let's round that up to 51 degrees. Okay, so why did I do that? Let me look again, back to, let's see, our whole page here. So 51 degrees is here. Oops, not here. Here. So I did that because in order to solve for this side length, I have to have that angle. There's no way out of it. I need this angle. So how do I get that angle? Well, let's not forget that the angles in a triangle sum to 180. So that means angle A plus angle B plus angle C all have to equal to 180 degrees. So I have angle A is 36. I now know that angle B is 51. So can I solve for C? Yes, I can. So C is 180 minus, was that 87? Minus 87. So C is equal to 93 degrees. Now that I know that angle, now I can finish off my equation and I can solve for what I actually wanted. So let's see. Sine A over A is equal to sine C over C. So sine of angle A is 36. Side length A is 5.9 equals sine angle C is 93. Now we know that over side length C. Good. Let's cross multiply. So remember, you multiply the numbers that are on a diagonal from each other. You divide by the other one. So C is going to be equal to 5.9 times sine of 93 all divided by sine of 36. So once you throw all that into your calculator, abracadabra, you get a side length of 10.02. So let's just keep it at 10. 10 units long. Did I have units up here? What are my units? Meters. 10 meters. Therefore, they are 10 meters apart. Awesome. So is that going to be the same answer as I have over here? No, it's not, because notice over here, we have a very definite obtuse angle in there. That is very definitely an obtuse angle. This one, my two bottom angles were acute. Here, my bottom angle is definitely going to be obtuse. So things are going to get set up the same way, but we're going to have to interpret things differently. All right, so in order to interpret things differently, so our sine A over A equals sine B over B approach that we did over here, we're still going to do over here. So all of this is still going to be the same. That's going to get us angle B equals to 51 degrees. However, that is definitely not the picture because that is not an obtuse angle. To get your obtuse angle, we have to recognize the fact that that 51 degrees is really there. So the obtuse angle that we're looking for, the obtuse angle ABC, right? So this inside angle here, that's going to be equal to 180 minus 51 degrees. So that would give us a totally different answer when we finish off our question, right? So minus 51 degrees. So that would give me an interior angle of 129 degrees. And that's going to change what we do over here. So let's figure that out. So I just brought my triangle over here to give me some space to work. So now we're looking at this triangle of 7.8 meters, 5.9 meters, and this angle in here is 129 degrees. I'm still looking for C, right? C, A, little a, big B, little b. We know this was 36 degrees. So my angle C, so A plus B plus C still adds up to 180 degrees, right? Angles in a triangle. Now I have 36 plus 129 plus C equals 180. So 36 plus 129 gives me 165 plus C equals 180. So let's subtract that from both sides. Minus 165 minus 165. That gives me an angle C of, what's that, 15 degrees? So now that's the angle that I would use in my final fractions. So sine A angle over A equals sine C over C. So sine angle 36 over 5.9. Sine 36 over 5.9 equals sine of 15 over C, which is what we're looking for. All right, so let's do our cross multiplying here. So the numbers that are diagonal from each other are going to be the ones that we multiply by. So C is going to be equal to 5.9 times sine 15, all divided by sine 36. So just throw all that into your calculator, and your side length is going to be 2.5979. Oh my goodness. Let's round that up to 2.6 meters. So therefore, in this scenario, they are 2.6 meters apart. 3 more. Some are 15 minutes, some are 25 minutes, somewhere in there. Between 15 and 25. I try to not go over 20. Yeah. It does happen sometimes, but I try very hard to avoid it.
So about 15 minutes, I'm going to put those up, get this boiling, cut some veggies, put some cheese on. I'll be as fast as I can.
Okay.
And put them in the oven for half an hour. Which I'll have to flip once.
Okay.
We go 10 minutes.
So I'm just going to bring you over here. So this is a nice little scenario that's been set up already in GeoGebra. Okay. And what we're dealing with is what's called the ambiguous case. So I can make my triangle be one triangle depending on my side length. If I make this side length a little bit longer, watch what happens. I can actually get the two triangles. So this is the scenario we were just in. That side length was long enough. I actually had two possible triangles, right? We have the one with the obtuse angle and we have the one with the acute angle. Now, if I make this side length shorter, I actually run into the scenarios where I have no triangle possible. So if I give you this angle here that has no side length defined on the side of it, and then I go side length, so it's a side angle. Notice how I actually have no triangle. I can have one triangle. Oops, if I get it exactly right. And then I can have two triangles. Isn't that neat? All dependent on how it's designed. And this happens for all of these wonderful little acute angles in here. Cool, eh? So let's just clarify what it is that we just saw. So we've got three possibilities happening here. If you're given the angle, this side length, and this side length, this is what we call the ambiguous case. Okay, so we can have their side length 1, their side length 2. So case 1, side 2 is too short. So that's the one that looked like and it just kind of dangles back and forth here and it doesn't actually go anywhere. Okay, so there's my angle that I give you. There's side 1, there's side 2. Case 2, which is what we did in our first example. Side 2 is long, right? So long enough to make two possible triangles. So that's the one where it looks like either there. So there's my angle, there's side 1. So side 2 can go here, or it can swing around and it can land here. So side 2 could be there, or it could be there. So one triangle is got 2 acute angles. And the other triangle is, oops, where this one is obtuse. Okay, and then last but not least, we have if side 2 is just exactly right, case 3, side 2 is perfect length, and it makes a right angle triangle. So I got my angle, I have side 1, side 2 drops straight down and makes a right angle triangle.